7. Grade 7 you looked at linear relations. Grade 8, grade 9. You really do a lot with it in grade 10. You might have just touched on it in those other 3 grades here. Essentially, after this tutorial, there's a few different things. There's sort of, 4 different things listed here, but quite a few ideas that are going to come up. Number 1 thing here is determine if a relation is linear or not. Not all relations are linear. That's where we're going to start, is talking about the differences. The Ma10 curriculum says students will learn about linear relations. It doesn't say it says they have to know if relations are linear or not, but it doesn't say we can show them what nonlinear are. So you're not going to see very many in the textbook graphs that are not linear, but we're going to look at some afterwards here. Second thing here is represent relations in a variety of ways. Not just linear, any kind, in a variety of ways. We're going to talk about afterwards what the different ways are. Number 3 here, third thing is explain whether data points, I think is what I meant in there, should or should not be joined or connected. You can put joined or connected there on a graph. I probably should have said on a graph after that, but you need to be able to decide in this year whether it makes sense to join the points or not, because there's a reason whether you would join them and what you're saying when you join them. And then we talked about this before, but identify the independent and dependent variables. Independent and dependent. Okay, so those 4 things. Before we start launching into some of the examples and stuff here, the first thing I'm going to do afterwards is have you write down some definitions. You can write it with your own words because we're going to discuss these things, but you can also use the textbook. And then there's some problems in here to do that you can work on afterwards. You can use the textbook in conjunction with this. You're going to represent the relationships in a variety of ways. We first of all are going to talk about things in general. Okay, so I'm going to just use some blank space up here. You can use your own blank paper if you want, or whatever. So first thing I want to talk about is linear versus nonlinear. Okay, linear relation versus nonlinear relation. These are 2 actually that came up in my other class. Somehow we were talking about bungee jumping, because when we were talking about things being related, somehow we got on the idea of bungee jumping. Oh, actually, I think that warm-up graph that you did, they thought of that as being bungee jumping. We were talking about whether that could represent someone bungee jumping. So at first they said, yeah, because you know, if this was your height, so not if this was Mark, if this was your height, some of them said, well, this could be the person's height off the ground, and this could be time in seconds or something like that, right? And this could be height in feet. Maybe, I don't know how you bungee jump from, but feet or meters. Meters, that's probably pretty high. But then we came to the conclusion that what would be happening for that first section? What would that mean? The person they're standing up on the platform being too chicken to jump off, right? But then after 2 seconds, either they stop being chicken or someone shoves them off. Hopefully no one shoves them off. But then what happens with so they're chicken for 2 seconds and then they decide, I'm going to jump off. But what would this be saying? Would this be realistic? In reality, can that happen? Well, while they're falling down, while an object's falling down, does it travel at a constant speed? Because that's what this means. A straight line means it's a constant rate. If I take something and drop it from a certain height, okay, I take some object and let it drop. Does it just drop at a nice constant rate like that? How does it drop? If I drop it from up here, what's its speed right when I let go? The instant I let go of the thing, what's its speed? You need an actual thing here. I better not drop that. What can I drop? Something? I'll drop this. A deck of cards. Deck of cards. If I drop this deck of cards here, what's its speed right when I let go of it, and what's its speed when it hits the ground? Is it a constant rate? Does it fall at a constant rate? It does? So if you drop from 2 meters off the ground, you're going to be going the same speed the whole time? Intuitively, no, because if we fall from farther, why do we get hurt when we hit the ground? Yeah, you're not going the same speed the whole time, right? You're not going the same speed at the top as the bottom. Otherwise, it wouldn't matter how far you fall from, right? Because you'd hit the ground with the same speed. You're accelerating, right? It's not a constant speed. You're accelerating. The speed is getting you're gaining speed as you fall, right? Otherwise, it would look like you're just kind of floating down at the same speed. If you have a parachute or something, that's different because that's why you have a parachute, to try and keep the same speed on the way down so you don't hit the ground and hurt yourself. So that's a problem. If we were really drawing this as bungee jumping, it would be more like this. It slowly curved down like that. Because the fact that it's a curve means it's not a constant rate. If it's a curve, it's not a constant rate. But then what's the problem with this for bungee jumping? Well, if you're falling at a constant rate and then suddenly, this would be wrong because you fall at a constant rate, suddenly, I guess if you hit something, that would be that the person didn't plan it very well and they actually hit something, and then you come back up at a constant rate. Really, if you were doing this, it would look more like that. It would curve down, and then you'd start to slow down at the bottom, and you'd come back up. You wouldn't come right back up to the top level, right? You'd come back up, and you'd slowly turn around, and you'd sort of level out in the middle somewhere. That's probably what it would look like. This is definitely not a linear relation. A linear relation is if you are traveling a constant speed, or the rate of change is constant. It has to be a straight line, which is what the word linear means, right? So if we have a couple graphs here, let's draw something that's not linear. So I drew you the bungee jumping graph because it would probably be something more like that. That's definitely not linear. If you want to draw another example of not linear would be, even if you just drop something, which we did before, even if you just dropped an object, it doesn't look like this, because that would say it's traveling at the same speed the whole time, and it doesn't. At the beginning, how fast is it falling? The instant I let go of that deck of cards, how fast was it falling? But right at the start. It has something to do with that. That's actually what it's going to gain as it falls, right? But the instant I let go of this, make sure we don't drop the computer, drop this instead. The instant I let go of it, it's hard to tell the instant, but right as my fingers are letting go of it, how fast is it moving? Not very fast at all, right? Really, it's not moving at all. I'm not throwing it down. What's making it go down? Gravity, right? So the instant I let go of it, it's not traveling anything. But then as time goes by, it starts to travel faster and faster, right? At the beginning, the slope is going to be that. Except it doesn't stay up there. It doesn't float up there. So it starts to go like this. It's getting faster and faster as time goes by. That's what a graph would look like. That's not a linear relationship either. Linear relationship, you need something to just constantly change. It's got to be a steady rate of change here. So let's make some more space here. And let's try and draw one other one here. So this is going to be something linear here. Let's say we started at 4, and then we had a line here that went like that. So if you have graph paper and you're actually trying to draw it accurately, I've drawn it so it starts at 4, and then it's for 2 squares over here, it's gone up 1 square every time. This goes 2 squares over, that's gone up 1 square. That's what makes it a constant rate when it's a straight line. If you look at a curve, this curve here for 2 squares over, it goes down 1, but then on the next 2 squares over, what happens? Is it still down 1? It's not down 1 there. What is it down now? It's down like 3 or something, right? Here I've gone 2 over and 1 down. Here I go 2 over again, but now I've gone down 3. That's not a constant rate. In grade 8, you looked at tables and you looked at the change had to be the same every time. This is 2 over 1 up, 2 over 1 up, 2 over 1 up. That's what makes it a constant rate. That's what makes it a linear function. Linear functions are going to have a constant slope. Slope is constant. How many people have heard the word slope before in math or in science? You might have heard it in science. The slope is a measure of how steep the line is. We're going to get to slope later on in this unit specifically, but basically slope is a measure of how steep the line is, and all you do is you compare how far vertically you go every time you go horizontally. You could say I go 2 to the right, and that takes me up 1. 2 to the right, up 1. When you're calculating slope, you happen to call this the run and this the rise. Okay, if you talk about a staircase, the horizontal part's the run, the stairs, and then you call these the risers, this part of the stair. You actually call these parts the treads of the stairs, but that's how far over it goes, that's how far up it goes. Rise and run. The slope is a measure of if you divide those two things. If you take the rise and you divide it by the run for a line, you get what's called the slope. We're going to work with slope later on, but it wouldn't hurt you to find out that that's what it is now. For something to be a linear relation, it has to have a constant slope. Anywhere I measure that, if I was going to measure the slope here, let's say I went from that point to that point, I had a rise of +1, and this is, what could this be here? Let's say that this was distance in meters. Distance in meters, and this is time in seconds. This is saying that I go +1 meters in 2 seconds. What's my slope? 1 divided by 2? What's 1 divided by 2? 0.5. This is actually a measure of something. This is called, what is that in this situation? What is that called? It's the slope, but it actually is meters per second. You learned in grade 8, you talked about rates. If you divide meters by seconds, you get meters per second. The slope of a distance time graph is the speed of the object. This is traveling at a nice constant speed because it's a straight line. Anywhere I measure it on there, it's going to be the same. Going up 1 for 2 over is the same as going, if I go 1 over, if I go 1 that way, how much up did I go here? How far up did I go? A half, right? I went 0.5 meters for 1 second. It's the same thing. I'm going to get that number anywhere I measure it. If it's not a straight line, I'm going to get a different measure. Here I got -1 for 2. Here I got -3 for 2. Okay, so that's the first thing to know is it's got to be a constant slope. Slope has to be the same. Okay, so we got one thing checked off the list. For something to be linear, straight line. We need to be able to tell from a bunch of different ways whether something's a linear relationship or not. So we need to look at the second thing here, which is looking at what different ways can you show whether something's a linear, what different ways can you show what a relation is? A mathematical relationship between two quantities. I got a list here for you of what different ways you can show things. I asked my other class, and the first thing they told me was the word chart. We're going to steer clear of the word chart because different people use that to mean different things. Microsoft Excel, they use the word, because the student was using the word chart to refer to a table, but things like Microsoft Excel use the word chart to refer to a graph. Those are both ways to do it, so let's not call it that. You can write a table for something. For that one that we just had here, okay, this thing right here, this is one way. This is a graph, okay? This is representing it with distance and time. So graph. There's graph, right? You could represent it with a table. I could make a table of some of the values on there. I could make a table of all these values here. Okay? If I was to make a table here, make some space. Let's get rid of my slope here for now. What would a table look like? If we created a table there for that, make a simple looking table for this. go back here actually first and rewrite this, give myself some more space. Why did I call that 4? That was kind of crazy. Can I stick with 2 here? Can I stick with 2? Because I actually, when I was thinking about the slope, I counted it as 2. I don't know why I wrote a 4 there. That was weird. Let's stick with that. If we're making a table here, we want that, and we want this. What would the points of my table be? I'm going to use 2 different variables here. For time, what would be a good variable to use for time? T would be a perfect variable. I'm going to put T for time here. What should you use for distance? D for distance. It'd be a good idea if you said what it was, but we know already what it is. If I'm going to put values in my table here, can I just put 0, 0? Does every relationship have 0, 0 as part of it? Does this relation have 0, 0 as part of it? It doesn't, right? What was the distance at 0? 2, right? So we got a 2 here. What was it at 2 here? What was the distance? What is it here? What does it look like from the graph? If you read this way? 3, right? 3. What's the distance at 4 here? What do we got here? 4. What's the distance at 6? Distance at 6, what is it? 5. Okay, so we got 2 things here. We have the graph and we have a table. That's 2 ways to express a relation. Graph and table. Okay? What's another way? What else was in my list there? What other ways can you express a relation or show a relationship between 2 quantities? What did I have in my list there? We had graph, we have table. You could make some kind of a diagram, I don't know, a picture or something. I'm not going to draw a diagram here, but the main ones here, you could use words. How would you explain that relationship between those 2 quantities with words? What's happening with these 2 quantities? How is the distance changing as time goes by here? How about if we say where distance starts? Distance starts at how much? Where does it start? What's the starting value for distance? 2, right? You're going to learn in this unit, one thing you have to learn is that the vertical intercept here, I would put down there somewhere, vertical intercept, often called the y-intercept, except I'm not calling it the y-intercept here. Why do you think I'm not calling it the y-intercept? The vertical axis, are we using a y for the vertical axis? What letter are we using for the vertical axis? D, right? You could call it the d-intercept, but then nobody knows what you're talking about. So sometimes it's called the vertical intercept. The vertical intercept is the starting value. Intuitively, you know this already, but people forget it in Math 10 for some reason. It's the starting value. Sometimes we call that the initial value. If I say, what distance did you start at here? I think most of you would say, you started at 2. Duh, it's right there, right? Whereas if somebody says, what does the vertical intercept represent in the situation? You say, I don't know. I never heard that question before. It's the same thing. What's the vertical intercept represent in any graph? It's going to be whatever the starting value is for this thing. That's something to know. Distance starts at 2 meters and then, I don't know, steadily or constantly increases. Steadily increases at what rate? At a rate of, how fast is it increasing? We wrote it out before. What was the rate here? Yeah, we had, I made it small here. We can make it big again, you remember? It's hidden right here. Look at that, there it is. You see it? 0.5 what? We had it goes 1 meter for every 2 seconds. Doesn't get the writing, you can't even see anymore, but 1 meter in 2 seconds, 0.5 meters per second. I'm going to put down here that it increases at a rate of 0.5 meters per second. Okay? When you have units that are something per something, they're a rate, they're a slope of something.